Hello people, Zach here again today, and today's video is going to be a programming video. I'm going to be talking a little bit about Rust, and this is somewhat of a reaction video to a video that was uploaded by Brian Lunduke regarding System 76's Cosmic Desktop Environment, which was written in Rust and apparently had a bunch of memory leaks. I'm going to explain why this would be the case in a language like Rust, which kind of touts itself on memory safety and the ability to prevent memory leaks. And this is kind of be a little bit of an in-depth, well, I guess a sort of a narrow explanation, I guess, of the language features that Rust is doing and why I think that Rust is overselling itself. So let's go ahead and get started. I think a good place to begin with memory safety, like what we mean when we say memory safety, would be talking about crashes. And really there's only one way that your program actually crashes, which is that there is a memory violation in some ways, like a segmentation fault or a paging fault. And segmentation faults and page faults are pretty much the same thing in essence. Basically, a segment or a page is a region of memory that has certain protections on your machine. And a fault occurs when you violate what those protections are. Like you're trying to access a page or a segment of memory that you aren't allowed to access, or you try to write to a page that isn't supposed to be written to, or you try to execute code on a page that you're not supposed to be able to execute code on. These would be the reasons why a segmentation fault or a page fault would occur. And when they do occur, what ends up happening is that it interrupts your program and then terminates your program, and usually the operating system will put an error that says what happened. So why do these particular types of errors occur in your code? Well, there's like four major reasons why it happens. One of them is the most obviously well-known one, which is a null pointer to reference. And the reason why this happens is because a null pointer, as the name sort of implies, is a pointer that points to the address of all zeros. And so when you try to dereference or access or write to a null pointer, basically what you're trying to do is you're trying to read to or write from the page, the memory page or memory segment that begins at address 0, which is not accessible, which of course interrupts your program and terminates your program. And the best way to work around null pointers to prevent it is usually to use something like an option type. So like say you can either be null or have a pointer to the value, and then in order to actually get a pointer to your value you have to unbox it and by doing a null check. That's usually the easiest way to go about it. Another way that you could kind of do it is you could have like a difference between a nullable and non-nullable pointer, so that if you have a nullable pointer, you can't, like, you physically just cannot dereference a nullable pointer. You have to like convert it into a non-nullable pointer, and that would be another way of doing it, because you can sort of guarantee as well that there would be no pointer to references. Now, the second type of error that would occur would be wild pointers. And basically what a wild pointer is a pointer to somewhere, or it's a pointer that you haven't initialized. So say for example if I declare a pointer and then I immediately try to pass, or I try to dereference that pointer, like say for example I have int star p and then star p is equal to 5, or sorry, is equal to 6. So this is syntactically correct in C, like there's no errors here that the compiler would catch. But what is the problem here is that I didn't actually specify what this p pointer is pointing at. So when I try to assign to the value that's at address p, it's dereferencing an uninitialized pointer, which is a wild pointer. God knows what it could be pointing at, and of course it's most likely going to cause a segmentation fault. Now on modern operating systems, like your desktop environment, for security reasons your operating system will usually initialize the memory to 0 for your declared things. So anything that's going to be in like your global scope would probably be 0, and if you're entering into a function for the first time it'll probably be 0. But if you're if you go down part of the stack depth and then come back up and then go back down, maybe it won't be 0. So this could still be some random value that was like garbage that was still on the stack when you re-entered into the function. And that's why I said it's a wild pointer, because it's just pointing at random crap. You don't really know what it's pointing at. And like I said before, the best way to just avoid this problem is to initialize your pointers before use. So in this case, we could have just said int x and star p is equal to and x. And so now when we try to assign 6 to p, we're actually assigning to this value of x here. And so now we've resolved this issue. So that's 2 different ways that we've prevented segmentation faults. One, we made sure that we can't dereference a null pointer by doing a null pointer check or by using an option type of some kind. 2, we made sure that our pointers were initialized before use. And so the next problem I'm going to be talking about, it'd be mutating memory through a pointer when the memory that you're pointing at, the pointer, isn't actually supposed to be able to be mutable. So in the C programming language, all of your memory that you're pointing at is considered to be mutable by default. So like this instar p means that sorry, I don't even know why I had to bother deleting what I had before. What this basically means, since we're declaring it as a regular int, is that this pointer right here that's pointing at the x is pointing to an int that's regularly variable. Had we declared this as const, in this particular case, this pointer would actually be pointing to a constant integer. So when if we were to try to do p is equal to 6, this would be an error. And the compiler should actually catch this, because we're trying to we declared it, the value type, as being const, and then we tried to assign to it. But what the compiler probably won't catch would be if we did something like that, and then int star p is equal to int star. Alright, so this is something that the compiler probably won't catch. The reason why is because we did an explicit typecast here, which means that there's no implicit conversion from a constant to an int. So this wouldn't be an error, but our pointer value here is variable, but it's pointing to constant memory. So we can imagine that this is basically going to be, this particular value right here is going to be in memory, probably in your row data segment, which is going to have write protections on it. So the segment or page that this particular variable resides on is write protected. So if you were to try to write to it, you would create a hardware interrupt that terminates your program, segmentation fault or page fault. But yet we create a pointer here and then mutate it. So like this is another issue. Like this is how you create a write access violation, which causes a segmentation fault. And like I said, the best way to prevent this is to just like make sure that your compiler doesn't let you do this. Like make sure it always explicitly requires you to don't let the compiler implicitly like convert from a constant, and a pointer to a constant value to a pointer to a variable value. Okay, sorry, it's hard tongue twisting my brain here. It's like 3 o'clock in the morning. So that's the third issue, and it's less of an issue. You don't see that a lot, but it's just something to be aware of. Now, the fourth issue is going to be dangling pointers. And so the best way to think about this, let's see if I had a struct. We do something like that, and All right, so it'd be something like this. So here we got this data structure that we've declared an instance of A, and it has this pointer value that's inside of it. And when we enter into this particular block right here, we declare a new object B, and then we create a pointer from A to this object B, and then B drops out of scope here, which means that B is now dead. But even though B is dead, which means that technically speaking its memory or resources that it would have had would have been freed, A is still pointing to it. So what we have here is a dangling pointer. It's a pointer to an object that no longer exists. And the way that you can kind of prevent this from happening would be that any time that you try to create a pointer that outlives the object with the lifetime that is shorter than the pointer itself, you just assume that that's an error. That would be just one way to go about it. So this is just lifetime checking. Like if you can ensure that you never create a pointer to an object such that the pointer's lifetime extends the lifetime of the object, then you can prevent this particular type of error. Now, why would a dangling pointer cause an error? Because again, it's sort of like a wild pointer. Because this A is pointing at this memory that's like, or this object that no longer exists, it's technically like a random memory. Like that memory could have been reused for something you don't know. So this is another cause of errors. Now, there's still one more type of, or one more way that you can create a segmentation fault, which is probably a little bit less obvious. So if you, and it all stems from array bounds checking. So basically, when you create, let's say you create an array on the stack, an array inside of a function. When you call a function, the local variables end up being allocated on the stack. So I might want to go into a little bit more detail here about what actually happens. So when you call a function, what ends up happening is it creates something called an activation record, and the activation record begins with the return address, and then it's followed by the parameters of the function that don't fit into the registers that are being used by the calling convention. And then after those registers comes your local variables that are inside of your function. But because the way that the stack works, the stack actually grows downwards from memory, from a high memory address to a low memory address. So what ends up happening is that if you were to, say for example, if I did val 10 is equal to 5, like this would be like a simple mistake you would think to make. Is like, oh, this is 10 items, so I can obviously address the 10th element. But because we're in a zero index language, the 10th element is actually 9. But because we access 10, what happens when we do this? Well, what ends up happening when we do this is that if we had a single value here, like if we had int x, or we would call this foo, just be sake of listening confusion, because we're accessing one element higher than what this actually allows, we would actually be overriding this parameter right here, this int x parameter. And then if we went to like 11, what we would be doing is we would be overriding the return address of the function. And once you overwrite the return address of the function, that means when the function returns, it could be returning to anywhere in memory. And this is actually a way that a lot of programs do exploits. But the big caveat here is that if you can return to anywhere you want to in memory, you could also return to an address that contains memory that has been marked as non-executable, which is how you get another segmentation fault. Now, you would think, well, oh, this is a huge security thing. And it's true, like it does cause a lot of bugs, like when you get to things like sprintf and whatever, but usually modern compilers, they have stack protections that prevent this. Like there's things they have called canaries where they can detect where you've tried to do a stack smashing and like it just won't let you do it. So it's not to say that we're completely helpless against this. Like we've had protections against this for a long time, but it's just a point that just to point out that this is how you get another kind of segmentation fault or page fault. So if we had array bounds checking, this would never happen. Like, we would never accidentally override the activation record by extending beyond the boundaries of an array that's allocated in a local variable. So that would be a solution to this. So now we have our major solutions, like 1, don't extend object lifetime references, 2, don't initialize pointers before use, 3, use option types or boxing to ensure that you always do null pointer checks, 4, don't allow implicit casts from mutable to non-mutable pointer values, and of course array bounds checking. So if we had all of these features, we could pretty much guarantee that you will never have a segmentation fault ever. And you will never have a paging fault ever. It's just not going to happen. The language would not be able to express that particular type of thing. It would be impossible. And so, in that sense, our language would be memory safe. And I think that Rust's feature set actually makes this the case. So it's memory safe in that sense. But what it is not memory safe in is being able to prevent memory leaks. And the reason why if this is actually fairly simple. So Rust's idea of memory safety is that we are going to manage the memory for you automatically, but we're going to do it through some like convoluted system based off of RAII. So it's an automatic memory management system, and there's different types of automatic memory management systems. So with RAII, it's actually the name is a bit of a misnomer, but RAII is that the idea that resource acquisition is initialization, which means that the object becomes valid the moment that you've correctly initialized it. But when people talk about RAII, they're usually talking about a certain aspect of it, which is the idea of objects being automatically destroyed when they drop out of scope. This is sort of like the example I gave earlier about B falling out of scope and then dying, and then A still having a reference to B. In RAII languages like C++ and Rust, every object will have a destructor, and when the object drops out of scope, the destructor function gets called. And so that function can be used to do various things. Like, you can use it to free memory, or you can use it to free resources and stuff. But this actually creates its own little can of worms. Like, say, for example, let me think about this. Let's do this in C++ like syntax, just so you can see what we're talking about here. So I'm writing while I'm laying sideways here. Hang on a second. It's like 3 o'clock in the morning. I'm not awake enough for this. Foo A. Drops out of scope here. Alright, so here's the example we're going to be going with. So we have this class, and it has this private field, which is called mem, and mem is just a pointer to some characters. And when the object is first created, we initialize that memory to a sequence of 4 bytes that we've allocated, which means that the object is now valid. And then when the object is destroyed, which means that which happens when it falls out of scope, we just free that memory. So just to make sure that we never forget to free this 4 bytes of memory that we've gotten. Well, now when we get down to our function here that we're calling it, we create an instance of A, and then we create an instance of B. Well, this instance of B here, because we've created it this way, instead of using a destructor, we've copied an existing object instead of just creating a new one. It didn't create any more memory, but what ends up happening is that it actually copied this pointer to this memory into B, and then when B drops out of scope, this foo function gets called on B, which frees the memory at the pointer that was pointed to by A when it was initialized. So now the A.memory, this memory, A still has a dangling pointer to this memory, even though this memory's been freed. So then when we try to access this byte by writing to it, we're writing to freed memory, which is just a crash. This is an issue that's just like inherent to this RAII system, that where we're trying to automatically destroy things that fall out of scope. And the only solution to this is that we can either create a copy of the pointer, like we can create a particular type of constructor that says, like, anytime that you try to do a copying operation like this, what we're going to do is we're just going to allocate the memory in order to create a copy of this instead of a copy of the pointer, a copy of the actual data. The other way to do it would be to use move semantics, which is basically like the second that we try to assign A to B like this, like B is actually given the pointer to this memory, and A is no longer has access to it. Like, say for example, we can have it set up in such a way that the second that this happens, B.memory becomes equal to A.memory, and then A.memory becomes equal to null. So now now all you'd have to do is say that if mem is not equal to null, then we would free the memory. And so if we had set it up in that way, then we wouldn't have a crash when A is destroyed, but we would still have the crash here because it's a null pointer to reference. So it's an iffy thing. Just the point that, like, we have to create these systems, like these copy and move semantic systems, in order to deal with the fact that, like, the destruction of the objects and the fact that we can copy them, just it can inherently leads to these invisible errors. And what's the other way that we can resolve this? Like, if we have to pass around these pointers to things and we don't want them to accidentally be freed, one of the ways that we can resolve this would be to use a more complicated automatic memory management system. Now, the way that C++ does this and the way that Rust does it is through reference counting. And this is where I think that the actual memory leak issue happened in Rust. So, if you're... The best way to kind of go into how this works, so, like, suppose we had a function, we'll call it foo, and we'll have... We'll say that I'm not going to write the code for, but I'm going to say that, like, we have these two objects. We'll call them object A and object B, and these objects are memory counted objects. So we'll call them RC objects. And the idea is that when they're first created, they have a reference counter that gets incremented so that it's equal to 1. And then the second we get to this point right here, at the end of this function, they both drop out of scope. And so when they drop out of scope, the reference count decreases, and so they both become 0 with their reference count, which ends up causing them both to free whatever memory that they allocated, just like with our previous case when we allocated memory and then we freed it when it is destroyed. In this case, they start off, the reference count for both of them is equal to 1, and then when we get here, the reference count is equal to 0, which means that we destroy them both. Now, if we had given a pointer to B, so like we said, A is equal to A and B, and this is just like a simplified like pseudocode syntax, the reference count of B would be incremented by 1. So now, so B would have, A would still have a reference count equal to 1, and B would have a reference count equal to 2. And so what happens when we get here, and both B and A drop out of scope, is that the reference count of A will equal 0, and the reference count of B will equal 1. So B can't be freed yet, but the second that A becomes 0, A becomes freed, which means that this pointer right here will end up becoming freed. So then what will end up happening is we'll have another line here where the reference count of B is decremented because A was destroyed, and so the reference count of B becomes 0, and then B becomes destroyed. So in this case, our automatic memory management system, everything's okay. Like, there's no issues here. Now we're going to go on to the third case, which is we're going to say that B is also going to have a pointer to A. Well, now what ends up happening is that A has 2 references counts, and B has 2 reference counts, and then when they both drop out of scope, their reference counts both decrease, but they both have a counter of 1, and guess what? Memory leak. This is what I think is happening with Rust, and the reason why it probably has memory leaks is because Rust makes heavy use of reference counting. Now, the way that C++ resolves this, it does something called a weak pointer, which is like, it's a pointer that doesn't affect the reference count, and until you try to convert it into a shared pointer, in which case it increments the reference count temporarily and then releases it. So, like, in that case, you would have like a strong pointer from A to B, but you would have like a weak pointer from B to A, which doesn't really work unless you have 2 different types of objects, unless you were giving them both weak references to each other. But I don't know, that can get kind of complicated, but it was just the point that, like, I think this is the reason why the memory leak issue happens. And the thing too is that there is nothing that Rust can do to prevent this. Like, there's no compile time evaluation of any kind that you could do that could prevent this problem from ever occurring. Because this is a logical error. This is not a this is not related to a syntactic thing or a semantic thing. Like, this is syntactically and semantically correct. It's just the it's logically incorrect, and there's nothing that you could do to fix that. And another issue that Rust can't do is, like I was showing before, with the classes and the memory that gets freed at the end of the scope. Now, Rust can kind of detect that particular case through borrow checking, because basically what borrow checking does is it prevents you from having pointer aliasing, where like you have 2 references to the same object that are at the same time. Like, it'll let you give a pointer to or reference to an object to a function, but then it like has to give it back, because the calling function is responsible for destroying the object. So it prevents you from ending up in a case like when A is having a pointer to B, and then B drops out of scope, and then A still has a pointer to it. Like Rust wouldn't even let you express that, because like you would have to give ownership to the thing. So anyway, the point is that the borrow checking system can guarantee that you're freeing your memory in cases where you're allocating memory for references and stuff, but that's only because the language has an understanding of references and pointers. That particular type of logic cannot be enforced on object handles. So, like, take for example a file handle on Linux. When you call the system call for file open, and it returns an integer, there's nothing about like an integer. There's no metadata surrounding the integer that would be able to tell you that, like, hey, you can't just like copy this from one struct to another, because we're gonna call the close system call when this object falls out of scope, in which case that thing's no longer valid. So like you have to like kind of forward think. You have to understand how these things actually work, because if you don't, you're going to be running into the same issue, because Rust is only guaranteeing that you're freeing your memory and not having a dangling pointer. It's not guaranteeing that you're freeing your resources and then not having dangling resource handles. So that's just like another issue. I think Rust is kind of overselling what it's able to actually do. And that's not to say that what they're doing is bad per se. It's good what it is that they're doing. In my personal opinion, I think that the way that they go about it is a little bit too obnoxious, though. Like, I would be fine if they have the features that are there and they just tell you when they think you're making a mistake. Like, if I'm trying to dereference an uninitialized pointer, tell me. Don't assume, unless I'm explicitly saying, no, this is what I really intended to do, then it matters. Like, if I'm trying to extend the lifetime of an object, maybe I have a good reason for doing that. Like, maybe the reason why I'm extending the lifetime of an object is because, like, I've decided that I'm giving it to this other part of my system. If I'm doing it explicitly, just that's fine. But if I'm doing it implicitly, then you can assume it's an error. Same thing would be like with borrow checking. Like, borrow checking is not inherently a bad thing, because when you don't have pointer aliasing, there are certain things that the compiler can do. Like, it can do vectorization of certain types of functions, because it doesn't have to worry about like there's an overlap between the different pointers. That's one thing that it can do. But at the same point in time, like, you don't want to have forced borrow checking, because if you have forced borrow checking, well, now you can't have pointer aliasing for things like linked lists, which are inherently have pointer aliasing. Like, you would want to have something sort of like the restrict property in C, but like the opposite of that. So like, maybe by default what you want is to have these restricted pointers that are borrow checked, but then in this particular context say that this is an unrestricted pointer, which means that we can alias this thing, and which means that the compiler just can't make that particular type of assumption. So it's like an inversion of logic, sort of like how in C++ everything has to be const correct, but then the reality is that you actually want everything to be like const by default, because otherwise you're just littering your code with const keywords everywhere. It'd be sort of like that. So there's a lot of improvements I'd make, but like my general philosophy is, if it's done implicitly, it's probably a mistake. If it's done explicitly, I intended to do it, and if I intended to do it, it wasn't a mistake. Anyway, that's pretty much it. Thanks for watching.